7-3, calculating portfolio risk. Here we get into the numbers. You are going to want to understand everything I say and practice everything I say in Excel. Let's create a portfolio with only 2 stocks in it. 1 share of Tesla Inc., 1 share of Apple Inc. First, we calculate the portfolio's expected annual return, which is easy. Second, we calculate the portfolio's expected variability, which is difficult. First, we calculate our 2-stock portfolio's expected return, which is easy. It is a weighted average arithmetic average. Okay, so Apple Inc. had an average annual return of 32% per annum from 2012 to 2021, and Tesla Inc. had 128% average annual return over the same period. 1 share of Apple stock is $142.41. 1 share of Tesla stock is $219.35. So if my portfolio consisted only of an equal number of shares of Apple and Tesla, let's say 1 share of Apple and 1 share of Tesla, and the day I buy these stocks, 39% of my portfolio is invested in Apple and 61% is invested in Tesla. Why? Because more dollars were spent to buy Apple than Tesla. So I take a weighted average of the annual growth rate of Apple Inc. and the average growth rate of Tesla Inc. over the same period. 39% of 32% plus 61% of 128% equals 90%. That is the expected annual return for my 2-stock portfolio, 90%. This was an easy calculation. Now we have a much harder calculation, a calculation you're going to want to try to do yourself. Find out where your errors are, try again, ask me questions until you can calculate portfolio risk or portfolio variance and standard deviation. Let's begin. We're going to calculate the risk of a 2-stock portfolio with equal shares of Apple Inc. and Tesla Inc. But in order to do that, we have to begin by getting the variance and the standard deviation of each of Apple Inc. and Tesla Inc. So this is one of 2 slides associated with getting the risk or standard deviation of our 2-stock portfolio. We begin by getting the standard deviation of Apple Inc. How do we do that? We put in the returns for Apple Inc. from 2012 to 2021, 31%, 5%, 38%, negative 5%, 10%, so on. We calculate the average annual growth rate, 32%. We assume that's going to be our expected annual rate of return on Apple Inc. in each of the years, 32%. And we calculate the variance by taking, for each year, by taking the expected return minus the growth rate, or the actual return, square it. So 32 minus 31 squared is approximately 0. 32 minus 5 squared is approximately 706, so on and so forth. Then we calculate the average variance for Apple Inc. by taking the total of all the variances for the 10 years and dividing by 9, which is the number of years minus 1 degree of freedom. That gives us our average variance. Sigma squared sub A is variance of the Apple stock of 1,065 percentage squared. Take the square root of that and we get the standard deviation for Apple Inc., or sigma sub A, is 33%. We repeat the process for Tesla Inc., and we get a variance for Tesla of 57,293 percentage squared, and a standard deviation for Tesla Inc., it should say sigma sub t, of 239%. Clearly, we can see that Apple Inc. has a much lower standard deviation at 33% than does Tesla Inc., which has a standard deviation of 239%. Why? Because Tesla is a much riskier stock, which also produces a much higher rate of return. And now the second and more difficult part of the calculation of the risk of our two-stock portfolio. We now have the standard deviation of Apple. We have the standard deviation of Tesla Inc. We need to calculate the portfolio standard deviation, a two-stock portfolio's standard deviation. How do we do this? We do this by building an equation or by building a matrix that captures that equation. What equation am I talking about? This equation. The variance of the portfolio is equal to 39% squared times the variance of Apple plus 61% squared times the variance of Tesla plus 2 times 39% times 61% times the correlation between Apple and Tesla times the standard deviation of Apple times the standard deviation of Tesla. This is how we calculate portfolio variance for a two-stock portfolio. Alternatively, from looking at the equation, we can look at the matrix behind the equation. That is the matrix I'm talking about, with stock 1, stock 2 on the left and stock 1, stock 2 on the top. Before we go any further, let's just remind ourselves what this 39% and 61% is. 39% is our percentage of portfolio invested in Apple, and 61% is the percentage of our portfolio invested in Tesla. We bought an equal number of shares of each, but Tesla shares cost more. Let's begin by looking at the 2x2 matrix. The 2x2 matrix includes the numbers 165, 774, 774, and 21,064. First, you need to know that along the main diagonal, that is from the upper left to the bottom right, the numbers 165 and 21,064, that captures variances for the individual stocks, Apple and Tesla. On the non-main diagonal, you have covariance numbers, the covariance between Apple Inc. and Tesla Inc., 774 and 774. And that this matrix is called a symmetric matrix because it is symmetric about that main diagonal. This will always be the case for this type of calculation. Let's start with the first term in the matrix, which is 165. 165 is calculated by looking at the equation. The equation says, the first part of the equation says, the variance of the portfolio is equal to 39% squared times the variance of Apple. So the variance of Apple is 1,065% squared. We multiply that times the percentage of our investment in Apple, 39%, and square it because we're in square units. We're calculating variance. That number that you get right there is 165. That was the first of our variance numbers. The second of our variance numbers is the next number on the diagonal, 21,064. How did we calculate that? Look at the equation again. The variance of the portfolio equals, that first piece we looked at, plus 61% squared times the variance of Tesla. Okay. The variance of Tesla, we know, is 57,293% squared. So we'll multiply that times 61% squared to get 21,064. If you do this calculation on a calculator and you get a slightly different number, it's because you are seeing rounding errors that would not occur if you had all the decimal places or if you're doing this in an Excel spreadsheet. All right. Then there's the covariance numbers, which are not on the main diagonal. Those are 774 and 774. They will always be mirror images of themselves about the diagonal. How do we calculate that? Well, first of all, there are two stocks, so we get if you look at the equation for variance of the portfolio and you skip all the way to the end, is the number 2 for two stocks. Then there is 39%, the amount invested in Apple, 61% the amount invested in Tesla, times the correlation coefficient between Apple and Tesla, which can be calculated using the correlation command in Excel. And we'll see, if you look on the bottom left, you'll see it's 42%. It says correlation of Apple and Tesla is 0.42 or 42%. They're positively correlated and they're modestly correlated. Then we need to multiply that times the standard deviation of Apple, which is 33, times the standard deviation of Tesla, which is 239. This number will yield 2 times 774, or 2 774s, which is what we see on our matrix. What I'm telling you is, if you add up all the numbers in our 2x2 matrix, 165 plus 21064 plus 774 plus 774, you will get the same exact number as if you did the calculation in the equation for variance of the portfolio. And what you will get in either case is 22,776 percentage squared, because this is a variance of the two-stock portfolio. Now, if we take the square root of 22,776 percentage squared, we get a standard deviation for our two-stock portfolio equal to 151%, which is a very significant standard deviation. Now, if you were to take a weighted arithmetic average of Apple Inc.'s standard deviation and Tesla's standard deviation, you would get a portfolio standard deviation of 158%. However, because of the diversification benefits of diversifying across two stocks in two different industries, it turns out that our standard deviation for our portfolio is only 151%, or 7 percentage points later than a simple arithmetic average. Let's see if we can see where the diversification benefit helps reduce the portfolio's risk or standard deviation as we increase the number of stocks. We'll do this over 2 slides, starting with this slide, where we'll be looking at a 7-stock portfolio. And the next slide, we'll look at a infinitely large stock portfolio. Okay, if you look at the chart, the matrix in the upper left corner, it looks familiar. Stock 1, stock 2 on the left, stock 1, stock 2 on the right. In the upper left, we have the percentage in the first stock squared times the variance of the first stock. In the bottom right of that 2x2 matrix, we have the percentage involved in the second stock squared times the variance of the second stock squared. And in both the bottom left and upper right, the non-diagonal numbers, they're exactly the same. They are giving you the covariance between the two stocks. Covariance can be calculated as the percentage in the first stock times the percentage in the second stock times covariance of the two stocks, or it can be calculated as percentage in the first stock times percentage in the second stock times correlation coefficient between the two stocks plus the standard deviation of the first stock and the second stock. Same thing. As we know, in order to get the portfolio's variance, we added up the 4 elements in this 2x2 matrix. And to get the standard deviation, we took the square root of that. This is what we did in the last slide. What happens as you get more stocks? Let's move over to the chart on the right. You'll see in the chart on the right, there are now 7 stocks. So we have stock 1 through 7 on the left and stock 1 through 7 on the top. What do you notice immediately about the number of elements in the matrix? All right, it has gone up to 49. It's gone up to the number of stocks squared. See, if you go back to the 2 by 2 matrix, there were 2 stocks squared, which gets us 4, the number of elements in the matrix. If you go back to the chart on the right, we have 7 stocks squared, gives you 49 elements, the amount of elements in the matrix. Stay with the chart on the right. The red squares are on what we call the main diagonal, and those represent the variances of the 7 stocks weighted for the percentage invested in each of those stocks. So what do all of these white elements represent? These white boxes represent? Those are covariances between the stocks. So if you were to look at the box 2, 4, the number 2 from the left, the number 4 from the top. Find the box 2, 4. That is the covariance between stock 2 and stock 4. Now go to 4, 2. 4 on the left, 2 from the top. Okay? And you will get the correlation between stock 4 and stock 2, which will be the same as the correlation between stock 2 and stock 4. Hence, you're going to get this 49 element, n by n, covariance matrix with the weighted variances along the diagonal and all the covariances between the stocks in the white. Do you notice something? Go back to our chart on the left. In our 2 by 2 cases, you had 2 cells devoted to variance and 2 cells devoted to covariance. Now go back to the chart on the right. The matrix on the right has 49 cells total. 7 of them are devoted to variances along the main diagonal, which means 42 of them are devoted to covariance numbers. The number, and do you remember how we're going to get portfolio variance? We're going to add up the sum of all the elements in all of the boxes, both white and red. So you can see covariance numbers are becoming a much higher percentage of the numbers we're adding together. Variance becoming a lot smaller. If we were to take this portfolio up to 100 stocks, now it will be a sea of white boxes, a sea of covariance boxes with only this one line diagonal full of variance boxes. Covariance is becoming larger and larger in our calculation of portfolio variance. And variance of the individual stocks becoming less and less important in our calculation of the variance of our whole portfolio. Now, what if we had a portfolio with n stocks in it? N is just some finite number. It could be very large. It could be 100 stocks. It could be 50 stocks. It could be 150 stocks. N is some finite number of stocks. Well, the portfolio variance is now going to be n times 1 over n squared times the average variance of the stocks in the portfolio plus n squared minus n times 1 over n squared of the average covariance of the stocks in the portfolio. The number to focus on here, the numbers to focus on here in that equation is n in the first portion of the equation and n squared minus n in the second portion of the equation. N associates with average variance, n squared minus n with average covariance. N in our 7 stock portfolio is n. N squared minus n would be 42 in our 7 stock portfolio, right? 7 times 7 gets you that 49 element matrix. Subtract out the 7 elements associated with variance, and you're left with all the covariance elements. So you can see the second of the 2 addends in that equation. It becomes more and more powerful as n gets larger and larger. Let's do a little mathematical manipulation. We multiply n times 1 over n squared minus n over n, 1 over n squared, times how to get the portfolio variance is 1 over n times average variance plus 1 minus 1 over n times average covariance. Now, let's let this become an arbitrarily large portfolio of stocks. Maybe it's 100, maybe it's 1,000 stocks, maybe it's 5,000 stocks. Like the Russell 5000, there's an index that has 5,000 stocks in it, or even more. Let's let the number of stocks go to a theoretically infinitely large number, infinity. All right? In that case, look at the second line. For the second line there where it talks about the variance of the portfolio, what would happen to 1 over n? As n goes to infinity, 1 over n goes to 0. So that entire first addend goes to 0. What happens to 1 minus 1 over n? As n goes to infinity, 1 minus 1 over n goes to 1, because 1 over n goes to 0. So effectively what you wind up getting, look at the very last line, the variance for the portfolio, if n is sufficiently large, becomes 1 times the average covariance, or just the average covariance of the portfolio. Earlier we said, as we increase the number of stocks in a portfolio, we're able to eliminate the specific risk from the portfolio and just maintain the market risk in the portfolio. Here we say, as we let the number of stocks in our portfolio get larger and larger, the measure of covariance within the matrix overwhelms the amount of variance within the matrix, which will cause a reduction in our portfolio's standard deviation, our portfolio's variance and our portfolio's standard deviation. That is the equivalent of reducing the specific risk in a well-diversified portfolio.